Well, good morning, everyone. Welcome back to Multivariable Calculus. It's such a blessing to be with all of you each day. Yesterday, I ended my morning and my eyes didn't hurt after looking at screens, and so I decided to stay with my studious blue light $8 glasses that my daughter bought for me. So we'll try them again today and see if it still continues to work. When we were together yesterday, we were focused on learning about two new coordinate systems, and we talked about cylindrical coordinates and spherical coordinates, but we didn't do any calculus. So today I wanted to begin by doing some calculus and trying to figure out how it is that we integrate in cylindrical and spherical coordinates. And as you may recall, the issue when we went from rectangular coordinates to polar back in the double integral world was trying to figure out what to do with that differential. And we ended up discovering that our dA in polar was equal to r dr d theta, and that r represented that scaling factor of the transformation. And so we might ask ourselves, what's going to be the differential element if we're in cylindrical coordinates and in spherical coordinates, or that is, what is that scaling factor going to be when we switch coordinate systems? And so we're going to start by playing around with cylindrical coordinates, and then once we figured out, do a couple examples of cylindrical, we'll switch over and talk about spherical coordinates. But I don't know about you, it's morning, and I find that in the morning, I'm always ready for at least one or two breakfasts. So I thought we could start with a little bit of food. Let's see how this works. So I have a can here of cranberry sauce.
Dusty?
Yep.
What section is this?
This is 16.5 part B.
Thank
We're
you.
continuing on in 16.5. So I have a can here of cranberry sauce, and I'm about to open it in my office, which is probably a guarantee that the rest of this class will be quite sticky. All right, so here we are. This is what our, can you see my shared screen now? Is that working? Yeah. Okay. Yeah. So here's the manipulate showing the differential element for spherical coordinates. And you'll notice this looks very similar to what we had in polar coordinates. And the area, as you may recall, of the differential element in polar coordinates was r dr d theta. Try that. Thank you. And so here we're going to have the same thing, but we're going to add another component. We also have some height or some thickness, and so we'll have a dz. And so you might expect, and quite reasonably, that the volume of the box, so to speak, is going to be an r d theta times a dr times a dz, and that does indeed work. Let me see if I can transfer my mold. Ooh.
Would you look at that?
What do you know about that? All right, let's try going back to the real life example. Every year,
much better looking.
Much better looking. Thank you for the suggestion. I think that was Robert. So let's see how this works. So we need to set some sort of radius. So we can imagine coming through and cutting like a little inner circle. So here's the center. And so you can think about the distance here as being like your r, and the thickness there being your d theta. Like the thickness on the outside is, wow, man, the light is terrible. I'm trying, guys. Where's my phone? Maybe we can get more light. Except for phones, flashy. Does that help? It's just the contrast. We're trying, guys. Okay. So, so the outside bit, this would be your dr. The inside bit, that would be your r. And then we could talk about the d theta, and that would be the angle that we're sweeping out. And then dz would be the thickness of the slice. So we could imagine just coming in and cutting it horizontally. I'm a little scared. I've never done this in class before. Let's see if it works. Boom. There's our differential element right there. Boom. Comes straight out of cranberry. So you might, I don't know if you guys like cranberry, but for me, when I think about differential elements, like I'm like, oh my gosh, like that sounds like
Very fun.
that sounds like totally sweet. A little bit sour bitter, but like I'm very thankful for this particular illustration. Although you might think that I'm a bit of a turkey for using this particular analogy. Okay, so you have this differential element here, and the key formula that you're going to need is that dv is equal to r dz dr d theta. Or if you want, you could swap it so you still get your r dr dz d theta. It doesn't really matter the order that you have here. And so this will be that differential element for cylindrical coordinates. And this r here represents the scaling factor of the transformation. And you can see that if we are looking at, if we're in the cylinder, that the size of that slice will be smaller if we're close to the center versus if we're farther apart. So small r, small differential element, big R, bigger differential element. And that's why we need to account for this scaling factor. Make sense? Questions? Very good. Turn my flashlight off. All right. Clean up breakfast or second breakfast. Let's see. So let's see if we can do some calculus with this thing. So I have a couple of examples in the work along. So let's see if we can look at the first one of those. Let me give you an overview of what we're going to do, and then we can actually work through the question by hand. So we started talking about triple integrals and spherical coordinates, and we ended with this formula that says that the dv is equal to the r dz dr d theta. And this r dr d theta part is the exact same thing as in polar coordinates. We just added the dz, sorry, the dz part because we added that dz because now we have a three-dimensional thickness to our differential element. So great, we've got our differential element, and now we can go through and find use the triple integral or evaluate a triple integral. And so in this first example, I give you the picture. And so I want to use triple integration in cylindrical coordinates to find the volume of the solid that is bounded above by the hemisphere z equals root 25 minus x squared minus y squared, and below the x is bounded below by the xy plane and laterally by the cylinder x squared plus y squared equals 9. And so we have this shape that looks something like this over here. The top is that z equals root 25 minus x squared minus y squared. The can around the outside would be x squared plus y squared equals 9. And that can has a bottom profile that looks like this circle. So let's do the math to set up and evaluate this particular integral. Okay. So what we notice is that our z values on the inside are going from the base, which would be at z equals 0, to the top of the silo, if you will, at z equals, it used to be square root 25 minus x squared minus y squared, but we recognize the x squared plus y squared in there can be replaced by the r squared. So we have root 25 minus r squared. And so our differential element is going to be r dz. And then we want to have a dr. We remember that we could project. So now we go from here. We project onto the xy plane. And we have this shape here. So it's a circle with radius 3. And so our r's are going to range from r equals 0 to r equals 3. And then we want the entire circle, and so our thetas are going to range from theta equals 0 to theta equals 2 pi.
Dusty,
Go ahead.
would it be improper to not have the theta equals r equals, but as long as you have your dz, dr, d theta in the right order?
So for example, having just that, or just this, like that?
Right.
Yeah, that would be fine. I find that it can help me to track what I'm doing by writing the variables, but you'll notice that sometimes I use them, sometimes I don't. It's okay either way. Good question.
Thank you.
In this particular question, we're looking for the volume. And so since we're looking for volume, what's our function that we're going to use? 1. Good. And then again, I've been just starting to use this vocab. What does the r represent here?
Scalar.
Not almost. Starts
Scaling factor.
Scaling factor. Okay, of the transformation, telling you that the differential element is changing in size. Do we need to go through and actually evaluate this integral, or are people comfortable knowing how to actually crunch through the triple integral?
Sure, might as well go through it.
Okay, we'll do this one and then maybe we'll just set up the next one. So I need to start by integrating 1r with respect to z. Which is going to give me rz from z equals 0 to z equals root 25 minus r squared. And this is now going to be dr d theta. And here you start to understand why I like to label my limits of integration, because if I look at the rz, I'm not sure what I'm substituting in for. Not that I can't figure it out, but this means I have to puzzle around a little bit less. Integral 0 to 2 pi, 0 to 3 of, looks like it's going to be r root 25 minus r squared dr d theta. Which, what is this thing? So 0 to 2 pi of 25 minus r squared to the 3/2. We're going to pick up a 2/3 up front. Is that it? Maybe in a 1/2? Like that? Do that right?
What happened to the R?
If I take the derivative, so I just took the antiderivative. So if I take the derivative, 2/3 times 3/2 would be 1. And that'll get me back to this part. But then I take, using chain rule, take the derivative of the inside. I'm going to get a negative 2r. Negative 2r times negative 1/2 would be positive r. Good? So, and we're evaluating from 0 to 3. So we put in 3, we're going to get 25 minus 9, 16 raised to the 3/2 power is 64 minus 25 to the 3/2 power, 125. 61. So we've got negative 1/3 times negative 61 times 2 pi, which is a funny way of writing 122/3 pi. Makes sense? How'd my, cool. I got 1 thumbs up. Other comments, questions about all of that?
Hey Dusty, I'm looking at your note right now, and this look the answer not the same though.
Clever. So where's my difference? I don't know which one's right. My scan notes or these ones? Let me look over here. 64. I think in my so in my scan notes, I think I get all the way down to the same place right here, but it looks like apparently I can't do arithmetic. I couldn't do arithmetic that day. 64 minus 125. What's that?
Negative 61.
Dusty,
Mhm.
I think the problem came in with the multiplying to by
Yeah.
61 away.
Exactly. So I think this is supposed to be a 122, right?
Yep,
So cool.
same answer.
Same answer, and thankfully a pretty easy to find mistake. So I don't remember who pointed that out in the notes, but thank you, and I will correct it online. So I appreciate the typo correction. Questions about this, or are you ready to look at another example?
Hey, Desi. I've got a little thing for problem 12 on the homework. It's very similar to this problem, and just like a little hint to the other members of the class, you can probably get, if you haven't done problem 12, pretty easily using this method on tomorrow night's homework. But just a small difference, so that's all I have to say for that.
Nice. So take careful note of these ones and then apply what we did to the homework. Is that what you're saying?
Yeah, there's a specific problem 12 on the homework, that is pretty straightforward if you use this method.
Nice. And I'm pretty sure that someone asked this question online. Maybe Vu asked this one online, and I think I responded somewhat similarly in a comment just this morning. So thanks for that comment. All right, let's look at another example. So I want to use cylindrical coordinates to evaluate this triple integral, and this time the triple integral is actually given in rectangular coordinates with all those limits. And so the first step is going to sort of be to try to figure out what this shape is, and once we figure out what the shape is, then we can probably convert the limits, right? Let me make sure you're tracking what I'm saying. That x squared we're going to be able to replace with what?
R squared cosine squared theta.
So that's going to be r squared cosine squared theta. Good. Okay. And the differential element dz dy dx is going to be replaced with r dz dr d theta. The challenge, the real question is, what's going on with these limits of integration? And it's not difficult to see what the shapes are, like what you could just change the values to, but simply changing 9 minus x squared minus y squared into something with r's might be good enough for the z, but it's not really going to help us on our middle set of limits. Okay, so let's kind of do these one at a time. So if we look at our z's, remember there's a z in both coordinate systems. So z equals 0 is going to be the same in both places. Z equals 9 minus x squared minus y squared. This can be replaced by 9 minus
R squared.
Negative r squared.
Yeah,
Negative.
very good. Very good. So that part's nice. But how about second, we've got so in this case, z was going to z. In this case, we've got xy going to r theta. And so we need to draw a picture of that corresponds to this part of the original limits of integration. So I'm going to draw a picture.
Dusty,
Go ahead.
quick question. Just as a guess, are we gonna draw a semicircle?
Yep, and this is actually a full circle.
Oh, okay.
And I had to cover it up. The reason why it's going to be a full circle is because we're going from the negative root to the positive root. So we want to look at y equals negative root 9 minus x squared. And that would be kind of the bottom half of a circle right here. And then we also want to look at y equals positive root 9 minus x squared. And that would be the upper half of the circle. Like that. And what's the radius of this particular circle?
3.
3, nice. Okay, and so in this case, we were given limits of integration from -3 to 3. And so we want the full circle, right? We're not taking just the right side, just the left side, just the top, just the bottom. We're taking the whole circle. So if we, from our picture, we can set up our limits. Where do our r's live between?
-3 to
0 and 3.
Say that again?
0 and 3.
0 and 3, that's right. And where do our thetas live? They live, I'll answer that one, 0 to 2 pi. So we can take all this stuff and put it together, and our integral I is going to be a triple integral. The z values are still going from 0 to now root 9 minus r squared. The r values are going from 0 to 3. The thetas are going from 0 to 2 pi. X squared is replaced by r squared cosine squared. And the differential element dv is replaced by r dz dr d theta. Let's see. how much I can get. Get about that much to show at one time. Questions about that setup or that process? Whew. So the thing that I want to point out about this, again, because I feel like it trips students up consistently, is that we were able to go from the Z, like the Z limits in the original to the Z limits in the new without a picture, because we were going from Z to Z, like it's the same Z. But in order to go from the XY limits to the R theta limits, you're going to have to draw a picture. Now it's possible that you're like, I've done this enough that you can visualize this picture and you don't need to write it down. That's totally reasonable, because this is a pretty common scenario. But there isn't a nice, clean algebraic way of going from these XY limits up above to these R theta limits down below. There isn't a formula that's going to do that for you. So whether you draw the picture or whether it just happens in your head, you've got to recognize that there sort of is this middle step where you're trying to unpack what these limits represent and what they must mean in the new coordinate system. It's sort of like when you pick up a map, you're traveling somewhere and it's unfamiliar, and you pick up a map, and the first thing you have to do is try to, like, twisting your map and trying to figure out which direction is north and trying to get oriented on the map. Where am I on the map? Which direction is north, or whatever it is. And once you're oriented, then you can start going forward. But kind of going from here to here is like getting oriented on the map. Like, what am I actually working from? And then go forward. All right. I don't know about you, but after doing all that math, I'm kind of hungry. And I've only eaten one breakfast during this class so far. So I thought maybe I would bring second breakfast. And the first one was light. So for the second one, I have a cantaloupe. And like, I want to eat the whole cantaloupe, but I'm going to wait until after class to do that because it'd be kind of rude to eat in front of you. So I'm just going to eat a small differential chunk. And so what I did was I sliced into my cantaloupe. And you'll notice that these slices would be, like these vertical slices, if you will, would be as though which of my spherical coordinates are constant. These would be like which coordinate. Let me ask the question again. There are three coordinates in spherical coordinates. There's a rho, there's a phi, and there's a theta. And so here I've sliced, I used my knife, and I came through and I sliced up and down like this.
That would be the phi, wouldn't it?
Ooh, I heard some difference of opinions. So is this the phis or
phi.
is this theta?
I think phi for the bottom part.
Sorry, I gotta point to which lines I'm looking at. I'm looking at, sorry, backward for me. That one and that one, there. Looking at these lines.
Yeah, that should be the phi.
Phi
Phi.
would be constant.
Phi.
Yeah.
This is the, oh, that's funny. This is the other phi. This is the phi called theta.
Oh.
Okay. This is theta. Why is it theta? Because if I want to figure out, imagine that right on the top, trying to rotate as hard on my brain. So I have an origin, and I have a circle drawn on the top. And if I want to make this work, you could imagine taking from the origin, or from the z-axis out, to find those vertical cuts. And
Dusty.
so that's my theta. Go ahead.
If I remember correctly, if phi were to be constant, we'd get like an entire sphere, right?
If rho is constant, you get a
Rho.
sphere.
Mm-hmm.
If phi is constant, you get a cone.
Cone.
If theta is constant, you get a plane.
Right. That goes through the z-axis, which is what you drew there, the z-axis.
Exactly. So these are my thetas. Theta's constant, which I hope helps you know that. How about the two horizontal lines, or like latitude lines, if you will? Those would be when phi is constant, because we're talking about the angle from the peak down to here, and then from the peak down to the bottom line. So this is phi. And then, so the angle between here, left, right, if you will, is the d theta. The angle up, down, that's the way it feels, is the d phi. And then the thickness of the cantaloupe, that would be our d rho. And so it comes out a little bit better in this light. And you can see that the shape of that inside surface right here is curvy, right? It's got a little bit of curve this direction, it's got a little bit of curve that direction, but even though it's curvy, the whole shape is, well, it's kind of like approximately rectangular-ish. And the smaller my d theta, the smaller my d phi, the more rectangular-ish it's going to be. But I hope you can definitely see that the rectangular-ishness of it is going to be dictated by how far out it is from the center of the cantaloupe. Make sense? Definitely a pro of doing class remotely is that if I have food in class, I don't feel the same obligation to share. I apologize for that, but yeah, I hope you'll understand. So let's look at this in the animation and see the same thing. So here's that same chunk of cantaloupe, and you'll see the d theta, here's our d theta, is impacting those horizontal slices like we were, or I guess vertical slices like longitude slices like we were talking about. And the d phi is impacting the latitude, so to speak. And the d rho is impacting the thickness, like the amount of meat of the cantaloupe that we actually get to gnaw on. It's like our favorite part of the eating. And so we again get this object that's a little bit rectangular, but we can definitely see that the amount that's rectangular is going to depend upon how far out it is and the various angles that are being swept out. So there's a nice, cool derivation of the formula for this differential element, but I think I'm actually going to just give you this formula, and I would be happy to derive it separately if you want to see it, or we'll play with it. I'll show you another way of doing it in our section that we're going to start next week. So here's the formula that you need for spherical coordinates. So dv is equal to rho squared sine phi de rho, doesn't matter which order here, de phi de theta. So it's dv is equal rho squared sine phi de rho de phi to theta. And this whole thing here, this rho squared sine phi, that's the thing that we're calling the
Scaling factor?
scaling factor, exactly. I can't spell. Scaling factor. So it's the scaling factor, and it should make sense that we need some sort of scaling factor, because where we are on the cantaloupe and how far in, how far out we are is going to impact the size of that chunk, right? So big rows represent far from the origin, and so it makes sense that that would make our shape bigger. Sine phi, that's going to tell you something about kind of the radius. Maybe, yeah, it tells you something about the radius of the kind of the inside of that chunk. We can do a longer derivation if you like at another time, but that's the formula that we're working from. Questions about this differential element formula, where it comes from, or are you ready to use it?
It's easier to learn by using, so.
Yeah, very good. Let's do it. Okay. So our question we're going to look at is the following. Use spherical coordinates to find the volume of the solid bounded above by the sphere x squared plus y squared plus z squared equals 16, and below by the cone z equals square root of 3 times the quantity x squared plus y squared. And conveniently enough, we have this picture, and the picture is of kind of this ice cream cone type of shape. It's a little bit not to scale because I had to modify it from the picture I was given, but one thing that you could notice about this is, let's see, how do I make this argument for you? Trying to make an argument for you that this angle here is pi over 6. I think one way of seeing that might be to try to create the triangle if we just looked at one plane. So maybe if we looked at the ZY plane, and so you can see there's the shape like that. Okay, and what would be the equation of this? If we're on the ZY plane, what would be the equation of this curve? Like the top of the ice cream cone, but this would be the top of the ice cream cone when x equals 0. So that would be
y squared plus z squared equals 16.
Thank you. Y squared. Whoa, scary equals there. Okay. No. Okay. And how about this line right, the other line? How about this one down here? When x equals 0, it'd be this expression.
That
there.
y squared is under that square root, right?
Yeah.
Y square root of 3.
So be
Y square root of 3.
Z
equals to y square root of 3.
Mm-hmm. Okay. And where are these going to be equal to each other? What's the z value here? So if I set these two equal to each other, I would get y squared equals 3, or y squared plus 3y squared.
Y equals to 2. Y equals
Yeah.
to 2 where they meet each other. Y equals to 2.
So y
Yeah,
equals
and
2.
if you plug,
That's going to make z equal to 2 root 3, right?
yeah, square root of 12, yeah.
Okay. So how do we, from that, do you see that the angle is root 6, or you don't see it yet? Maybe if we did the arctangent, so the tangent of, here's phi. So the tangent of phi would be the opposite side, which is this length, which is what?
2 square root 3.
2 root 3 is that height.
2, just 2.
Just 2. See if you can see it. Right. This length here is that value. So the opposite is 2. The adjacent side would be 2 root 3. And so what that would tell us that tangent of phi would be 1 over root 3, or I think that gives us that phi is equal to pi over 6. Is that people okay with that as an explanation for why it is that we can claim this angle is pi over 6? That was not a convincing yes, but it wasn't a question either.
Dusty,
Mm-hmm.
which equations did you set equal to get that 2 square root 3?
To get this 2 square root 3?
Yeah, just which ones? I mean, there's a whole bunch.
There's a bunch of equations there. I found the 2 first by substituting, basically, I need more colors.
Just
Okay.
x equals
Yeah.
to 0 in both equation and just equate both.
Yeah. So I have these two this equation and this equation here, and I can set these two equations equal and look for the intersection point, and the intersection point would be there at 2, 2 root 3.
Okay, makes sense. Thank you.
Good question. Other questions? Very good. Very good. So all that's trying to understand the picture. And now we want to go ahead and set up an integral. And so we're trying to use spherical coordinates to find the volume of the solid of the ice cream cone, bounded above by the sphere, x squared plus y squared plus z squared equals 16, and below by the cone, z equals 3 square root of x squared plus y squared. So this Sharpie's about dead. Okay. So our volume is going to equal a triple integral. And since we're doing volume, what's our integrand going to be? What's our function here going to be?
1.
1. And then because we're going to use spherical coordinates, what's our differential element?
R dz dr d theta?
No, this is the new one.
Wouldn't it be
Rho squared.
Sine.
Phi to rho to phi to theta. So we can start with our rhos. Okay. And so when you look at the picture, remember rho starts at the origin and then works its way out to where it comes out of the ice cream cone. It's like a straw going into the shape. Right on the edge, it would just track along, it's right along the cone, and then comes out. Go up through the middle and pop out. And so it's going in at 0 at the origin, and it's coming out at the top of the cone, which would be at rho equals, do you remember what the formula was for, you had x squared plus y squared plus z squared equals rho squared. I think this is going to be 4. Let me explain that for a second. This was x squared plus y squared plus z squared equals 16. All that garbage is rho squared equals 16, or rho equals 4. Okay, so our rows are going from 0 to 4. Our fees, we just worked with our fees just a moment ago using all that trig. We started at the z-axis and we worked our way down. We discovered that our fees are going from 0, that's the z-axis, down to phi equals pi over 6. That's the edge of the cone. And then the good news about ice cream is that it looks the same from every direction. That's why we're always spinning it while we're licking it, trying to keep that nice uniform feel. And so our thetas are going to go from 0 to 2 pi. And this would be the setup for a triple integral using spherical coordinates of the volume of an ice cream cone with this particular shape. Questions about this?
So if we're always dealing with like a full cone, we could always say that theta is always going around a full circle.
If you had half a cone, if it ran into like a butcher or something that chopped it in half, if they chopped it like up and down, then you'd have maybe your thetas from 0 to pi or something like that.
Butchers don't do that, barbarians do.
Good point. If you ran into a barbarian that had a very sharp knife, then you might have your thetas from 0 to pi. Very good. Very good. Cool. There's a lot there. On the one hand, you can see that you're going to have to bust out some trig. You're going to have to be careful. But on the other hand, you see that it's just an extension of what we did with triple integrals, which were an extension of what we did with double integrals, which are basically the same thing as we did with single integrals. So it's a little bit more complicated because the pictures are more complicated and there's variables running around all over on you. But really, this isn't new. It's just a new application of something that you've done in the past. So as we wrap up for the day, I wanted to wish you a day as healthy as a melon that you might have eaten for breakfast, and interactions as sweet as the ice cream cone that we all wish that we could have for lunch. So have a wonderful day. I'm happy to hang around on the line if you have any questions. But in the meantime, that concludes our class. Take care, everyone.
Thanks, Dusty. See you tomorrow.
See you.
Thank you.
Dustin,
Go ahead.
I wanted to say that I appreciate your humor. It's so subtle, yet powerful.
Thank you. I appreciate that. I appreciate that someone laughs or smiles. It's funny to gauge response when you can't see people. So I appreciate that.
Cheers, and thanks for the lecture.
Yep. See you tomorrow. Vu, Joseph, Robert, questions?
No,
I know
so we'll see you tomorrow.
Sounds good. Thank you. Joseph?
I know I had homework questions.
Cool. Let me
Because on
pull
like
that up.
on number 10, I got to the last attempt, And so I was like, oh, okay, I have one more attempt. I'll just move on and continue working. And so when I moved on, it counted my my
Nice.
last attempt.
Let me see.
So I was wondering if you'd be able to open it up for one more, so that way I could actually.
And you tried
was-
it. Well, let me see it.
Yeah.
This is triple integrals, right?
Yeah. Number 10. I get so confused on them. It's always just trying to find solving the integrals, of course, no problem, but it's always getting the limits is the hardest part.
Right. Totally. So this is the right question?
Take a look. I think it's the right question.
Cool. So you tried it twice, and then it was the third time, and that was what was giving you fits. Is that right?
Yes.
Okay. So I think the way the system works is if you go on and use your last attempt, you should be able to come in here, and I don't remember what you push, but it should give you a new question, and it'll just change the numbers a little
Well,
bit.
no, that's the thing. I already ran out of all those attempts.
Oh, so
and
you
like
burned
I
it.
got to the last one, and it's like, oh, okay, so this is the last one. So I went and moved on, but it's when I moved on, it counted my submissions. Like it wouldn't let me move on unless I finished the question.
I'm tracking with you. I'm not sure. Let me see if I can figure out.
Yeah.
Like,
I also want help with this question too, of course.
yeah, of course. I'm just trying to remember your reviewing homework. Trying to figure out what I can do as an instructor. I think I can give you a 6th attempt.
Yeah.
Which there might be a better way of doing it, but that's probably the easiest way.
Yeah, I think
that I
that's
can
the
do it.
best way.
Does that work?
Yeah. All right.
Cool. Do you want to look at the question now?
1 second. I need to reset the whole thing. Okay. Yep. Now I got the similar question.